Okay, so this year we are skipping how to do the second derivative parametrically. That was on Friday, and then the homework involved a lot of the second derivative. So Rowan, a lot of people were mad at me at the homework assignment because I couldn't do it. Looking at Calc Chat, a lot of different things. I thought there was only maybe one problem that was second derivative based, but a lot of them were. So you need to know how to do first derivative parametrically, which involves dx dt and dy dt. How do you get slope in rectangular if you have dx dt and dy dt? Good. Dy dt over dx dt is slope. How do I get speed parametrically? Dx dt squared plus dy dt squared square root. That's speed. And the whole thing for the next like 10 slides is how do I get arc length? And arc length is just the integral of speed. Middle school math, the speed would always be on cruise control at 60 miles an hour. So you'd go for 2 hours, 60 miles an hour, you went 120 miles. And the harder question in middle school would be like, for 30 minutes I went 50 miles an hour. For 30 minutes I went 70 miles an hour. How far did I go in the first hour? Still, it averages out to 60 miles an hour, but that's where you worked on like weighted averages. Now though, I'm going 50, then 51, then 52, then 53, then 54, now 55, 55, 55, 56, 57, and it keeps changing. That's calc based. That's where you're going to integrate over that time period. And when you integrate, I want to make sure you guys know it's not the green route on the board, it's the purple route. So it's not how far horizontally it goes. So if you watch baseball and they hit a 400-foot home run, they're describing the green 400-foot home run. If you are watching Tiger Woods golf and he hits it 320 yards down the fairway, that's green length. Arc length is the purple, the actual path of the ball. Okay? So, in today's notes, just to let you know, there is a lot in here that I don't do because I'm trying to lure you into lunch. So I have 3 AP problems. We'll do one. There's 2 more that you can do at lunch. If you don't do it at lunch with me, totally fine, because right behind it is the answer key. Okay? Arc length. There are a lot of different integrals for arc length that we could do. I'll do a couple of them with you in class, and then the other ones you'll do at lunch if you want, or look at them at home because they're just set up. There's 2 homework assignments tonight, arc length and polar. So the black and the blue. A lot of the blue homework is already done for you in the homework or in my notes as well. So like there's a lot of stuff that I don't cover today, which is just referencing for you for lunch or after school or at home. You can just take a look at my work. Okay? All right, so first thing on arc length, I don't think you need to really write anything down here. I just have a lot of different random notes. Speed is the Pythag part. You're used to distance equals RT, and the issue is what happens if the R changes nonstop. Well, that's the calc way of D equals RT, and the way you handle D equals RT in calc is it turns into the integral. Okay, so if you want, you can think speed is the blue version of dVA. I've always color-coded the dVA as black, blue, green. So the speed part, you could think of it as the blue, which now makes me think I need to turn this to blue, which means I should probably turn this to something else. But now that I turn that to something else, I need to turn that back to something. Wow, my color's way off. There we go. So I'm giving you the speed. If you integrate it, you get up into the arc length sector. Okay? So let's look at one here with this guy. Okay. So I want to find the arc length around this circle. Geometry tells me the radius is A, so it's 2 pi r, so the answer is 2 pi a, which I totally agree with. But I want to look at it parametrically. Now, parametrically, you're used to time, so you're used to a t variable. A lot of times you can get away with the t variable being a theta variable. So in this case, it's kind of saying whatever angle you're at that time. So if you're at 30 degrees, that would be at 30 seconds. Now, I shouldn't really say it that way. I should do it in radians. So if you're at pi over 2, that's at 90 seconds. If you're at pi, that's at, I did it again. Sorry. Yeah, I did it again. Thanks. Good job, Bach. Okay, if you're at pi over 2 angle, which is 90 degrees, you would be there at pi over 2 seconds. If you're at pi angle, which is 180 degrees, halfway around the circle, you'd be there at 3.14 seconds. And it will take you 6.28 seconds to go around the whole circle. And going around the whole circle will be the whole circumference that I want. So we can do this based off the arc length formula. I know the answer is 2 pi a, but let's get that using the formula. So what's dx dt and what's dy dt? Or in this case, what's dx d theta and dy d theta? Go, out loud. Tell me. Okay. Yep. And then I get to plug those into the speed formula into arc length. So I have 0 to 2 pi. That 2 pi is saying it takes me 2 pi seconds to do this. So 0 to 2 pi of that speed formula. And now we got to integrate it. Okay? This is the easiest integral because a lot of that goes poof away. So if you square this out, I get a squared sine squared plus a squared cosine squared. And then from that, I just factored out the a squared. So if you want an intermediate step, you would have had a squared sine squared theta plus a squared cosine squared theta. And from that, I just factored out the a squared. What happens with sine squared and cosine squared? 1. So now I'm left with the square root of a squared, which is just a. So in this case, this is like a middle school math problem because you are at a constant speed of a the entire time. So if I'm at a constant speed of a, I can do distance equals rt. My r is the a, that's how fast I'm going. And the t is the time it takes, which is my 2 pi. So I go 2 pi a total distance, which is what you knew already from the circumference. So that one was not trying to trick you. That was just kind of you starting to walk through arc length formula. Very rarely does the speed turn out to turn from that formula into a constant. I did that one on purpose because I wanted you to just get used to it. The next one will not be as easy. But are you guys okay with that? Especially since you knew the answer from geometry up front. Now, we're going to look at this one. Okay. Again, up front, I put them in theta world, but you can have called those t's if you wanted. So is that a variable or a constant, the theta? Is it a variable or a constant? Variable. Okay, I screamed at first hour today because they wanted to say it was a constant here. And I'll tell you where they try to tell me it was a constant. They tried to think those were constants. So then when they took the derivative of the blue and the orange, it was not a product rule. They wanted to just kind of say it like the last problem where it would have been like, for the blue guy, theta cosine theta. Or for the orange guy, since it's negative theta cosine, it would have switched signs and it would have been theta sine. And I screamed at them because I told them, you cannot tell me those two thetas are numbers, but that theta, and that theta are variables. If you want to call them numbers, what's the derivatives of all of that? 0. And do I move at all? No. And how far did I travel? None. Because if you told me those are all thetas are numbers, the derivatives of all of those would be 0. And 0 squared plus 0 squared square root integrate would be 0. So I told him you can't pick and choose and call the purple thetas numbers and the green thetas variables. All of those are variables. So when I'm about to ask you to take the derivative, you will be doing a product rule inside that. But before we do that, I want you to visualize the shape. This is kind of a cool shape. I think of it as kind of like tetherball at the elementary schools. So think of the middle as kind of your rope wrapping around the pole. And I can unwind it, or if you hit it really hard backwards, you can rewind it back up if you ever played tetherball. Okay? Over time, or over theta, your rope gets bigger and bigger and bigger as it loops around. Okay? So I want you guys here to take dx dt, or if you want to call it dx d theta, take dy d theta, and I want you to integrate from 0 to 2 pi and show me what you got. Okay, see how much rope is there on this spiral. So try this out. So this one here was still a decently nice one. Yes, there's a big product rule blob for the blue and the orange. Yellow and green go straight to a basic trig guy. What's nice though is yellow and blue merge to something simpler, and green and orange merge to something simpler. So then when I integrate, this feels like the last problem, but instead of a out front, it was a cosine, or sorry, a theta out front, which simplifies to this. So your speed is not constant. Your speed is changing over the time, but whatever time you're at, or angle, remember t is theta here, whatever angle or time you're at, that's your speed. So at time 0, no speed. Time 1, 1 speed. Time 2, 2 speed. Time 3, 3 speed. What is constant here? Not your speed, but your acceleration. Your acceleration is 1, because if you took the derivative of that theta, you would get 1. So you're constantly accelerating in this process. Last problem, you had a constant speed of a, and I guess a constant acceleration of 0. This problem, you have a a speed of theta, which is constantly increasing at an acceleration of 1. How's that one so far? Okay, so here's what I mean by, here's some notes where you can do a lot of practice on your own. Next problem, don't do it now, but this is a good practice on U sub and seeing how you can handle U sub after some algebra. And then next problem involves crazy derivatives with ln and arc sine. And then once you get down to it, can you get a common denominator? Once you go through that, can you integrate this guy using either partial fraction decomp or trig sub? All of this is prior content. I then show you, what do I show you? I show you on the next slide partial fraction decomp. Doesn't mean that's the way you had to go, but I got you down to a nice looking answer. Stuff you can do on your own. Okay, and then here's the arc length homework for tonight. And I solve 47 here. And then I solve 51 here. I guess I didn't solve it, someone else solved it because their handwriting is nice. Okay, so if you have questions on stuff, half of your homework's already done for you in the world of arc length. Now, here's one where I want you to go to the boards. This is the kind of a summary question from, this is a summary question of Paremetric that you'll see on the AP test, or that you'll see on my test a week from today, or a week from tomorrow. Okay, first note, it's Paremetric, and it's on the calculator. You can do all of this on the calculator. So you can go to the boards and hang out with people and try this out, but you can do all of this on the calculator, but you don't have to do it in the parametric mode. I can do all of this in the rectangular mode. So when you see, like in rectangular mode, when you type in X, what's your brain thinking it really means? T. You guys okay with that? Last question, just read it for a second so you can see the word. Find the acceleration vector. All that means is give me the second derivative of X, comma, the second derivative of Y, both in terms of time. You know how on Friday I said I'm not doing second derivatives. What am I not doing second derivatives of? What form am I not doing with you guys? The second derivative form of rectangular. How do you get dy dx? Hurry, I got 3 seconds. dy dx is dy dt over dx dt. How do I get second